Okay. So now we're finding find So before, the molar ratio we needed was between the two reactants. This time, the two things the molar ratio will involve is the limiting reactant we found and then the product. We're using the limiting reactant to predict the product. So in this case, get rid of this. Now this ratio is going to be F2, so there's 2 moles of F2 to 1 mole of TiF4. And we're going to need to come up with grams here. So we're going to need the grams per mole of the limiting reactant, and we're going to need the grams per mole of this. The grams per mole of the limiting reactant is this. That's our limiting reactant. So we're kind of done with that. The grams per mole of TiF4 is going to be 19 times 4. So we get 76 from the fluorines, and the titanium is 47.88. So it's 8. Do that right, I feel like it is. So it's 47.88, 123. 0.88 grams per mole. So, grams of TiF4 is 1 mole. So I'm going to need that as well. So that's just finding the molar mass of TiF4. So you're going to need those two things. So yeah, grams per mole for product. So those are the things involved in calculating the theoretical yield.
You need to find the molar mass of the product.
That's the molar mass of the product.
But do you need to find it and find the theoretical yield?
Yes. We're finding the theoretical yield in grams.
Okay.
And since we're going to have to find this in grams, that means we're going to need this.
Okay.
So it's these three things that we're using. All right, and like I said, you have to use the limiting reactant to predict the product. So I'm going to start with this, the limiting reactant, 126 grams. Grams of F2, grams of F2 on the bottom. The only one of those three things that mentions grams of F2 is this. So it's 38 grams of F2. 1 mole of F2. Now we're going to use the molar ratio. We need mole of F2 on the bottom. We've used that one. We have these two left. Of these, which one of them mentions moles of F2? The only one that mentions moles of F2 is this one. So 2 moles of F2 to 1 mole. And now we need moles of TiF4 on the bottom. But of course, we've used this now, so we're down to this. 1 mole of TiF4 That's gonna do it. What I'm calculating here is the theoretical yield, which is what we've been after this whole time. And it's 1.6 times 123.88 divided by 38 divided by 2. It's two significant figures, and I got 2.6. And that's the answer. That's the end of it. We found the theoretical yield. 62 doesn't say anything about an actual yield, so there's nothing else to do. It just asks us for the theoretical yield. Admittedly, it's a long walk, but that's how it's done. You guys okay? What's next? I'll do 64. I think 62 is like 64. Maybe 65 is like 64. Maybe I want 63. Looking around in another chapter. Yeah, 65 is likely 64. So I'm going to do 64. You guys get the answer at 65. But let me do 64. Okay. No, that's asking me. No, I don't want to do 64. 66. Don't do 64. That's an easy twist, but I don't want to focus on it yet. 66, 67, and 68. I'll do 68, 66, and 68. All right, then 66. 7, 66. Here it is. Okay. I'm going to do 66, not 68. So, did I say 66? What did I say? 64. Don't do 64. Okay, moving straight on to 66. looked up on the periodic table already. Mg off the periodic table is 24.31 grams per mole. Oxygen is 16 grams per mole. All right. The equation is the reaction 2Mg plus O2. That's the reaction. We have to do this. Oh, well, let me mention this. It says there's 13.1 grams of Mg is put in, 13.6 grams of O2 is put in, and it says at the end of the reaction, 12.4 grams of this is collected. They're saying someone actually did this reaction, and this is how much MgO they got at the end. They don't specifically say that that's the actual yield, but they did say it essentially, this is the actual yield. That's in the phrasing of the question. It says someone put this and this into the reaction, and when the reaction was done, this is how much MgO they got. That's an actual yield. Nobody calculated that, someone just went to the lab and did it. But we need to calculate the theoretical yield, what we should get in this reaction. It's typical that you get a bit less, sometimes a lot less, depending on the method you do the reaction with. The actual yield is generally a reflection of the process used, the method used for the reaction. With a different process, a different method, they might get a much better yield than that, but that's going to end up being very low compared to the theoretical. So the question here, what was the percent yield of this reaction? So you've got your actual yield, we've got to find our limiting reactant, then find our theoretical yield, and then we'll use the actual yield to find the percent yield. All right, so at the beginning, we have to find the limiting reactant. So what do we do?
Pick the first,
Pick
whichever
one.
one.
And I always just pick the first one. Doesn't matter which one you pick, but I'm going to go 13.1 grams Mg since it's just Mg, that means it's 24.31 grams of Mg is 1 mole of Mg. It's not a formula, it's literally just the atom. So you can get that straight off the periodic table. Mg is 24.31 grams is 1 mole of Mg. Next, we need the ratio of the two reactants, molar ratio. We're going to need moles of Mg on the bottom. So that means 2 moles of Mg to 1 mole of O2. Because here we're comparing the two reactants. And now we're going to need the moles of O2 on the bottom. This is a molecule with exactly 2 oxygens in it. So that one's just 2 times 16. So that one will be 32.00 grams of O2 with 1 mole of O2. So we're using that. 1 mole of O2, 32.00 grams of O2. And again, this is what this problem tells us we have. This is what we need. So if we calculate that, 13.1 times 32 divided by 24.31 divided by 2, and I get, this will be 3 significant figures, exact, 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 exact. Four significant figures, 4, 3, so we need 3, and I get grams of O2. Grams of O2. Here's how many grams of O2 we have. Here's how much we need. So what's your conclusion?
It's excess.
It is excess. We have more than we need, so it's excess. And that necessarily means that's the limiting reactant. So we identify the limiting reactant. If I did this with O2, if I did continued across, I come to the same conclusion. You want me to do this one? It's superfluous, but I'll still do it. It's just to show you that you come to the same conclusion. At the end of this, we'll have how much mg we need, and we will find out we don't have enough. We won't have 13.1, we'd have less. And then we'd go, okay, that's limiting, which necessarily means this one's excess. All right, but I won't do the second one, just to save time. Like I said, you'll come to the same conclusion. You come to this as your conclusion. So now that we found the limiting reactant, our process now is to find the theoretical yield. Limiting was mg, so just to save a little time, I can actually leave all that there, because the way you start, now that I need to find the theoretical yield, and this is limiting, I'm going to start with 13.1 grams of mg, and then 24.31 grams per mole. But now the molar ratio is going to be between the limiting and the product. So I've got 2 moles of mg and 2 moles of MgO. And that means I'm going to have moles of MgO down here. I haven't calculated it yet, but MgO is just 24.31 plus 16. Right. 1, 3.
How come you multiply 24.31 by 2 if you're finding the molar mass?
I am going to multiply these.
I'm for the.
There's 1 mg and 1 O.
Oh, the 2 doesn't.
So I'm just going to add these 2 together. I mean, if I did it sort of formally in the way I did before, I would go mg, there's 1 of them, O, there's 1 of them, mg is 24.31, oxygen is 16.00, but this comes to 24.31, this comes to 16.00, and then add them up. I just skipped all that.
Mr. Eddy,
Huh?
for the actual yield, so you found the limiting reactant, and then you found the theoretical yield, and then using the grams that you found in that, this is what you're expecting, you just add them, and that's the actual yield. And then you use the actual yield to find a percent yield.
Actual yield is given in the problem. This is literally given to us in the problem.
Oh, okay.
Let me show you that, because it's in the phrasing. When 13.1 grams of Mg reacts with 13.6 grams of O2, 12.4 grams of MgO is collected. That's telling you someone actually did this and collected
I
this.
see.
That's what tells you this is actual yield. And that's kind of why I put parentheses and said is collected. That's the actual yield. We're about to calculate the theoretical yield.
I see that. Thank you.
So I got the molar ratio, and now I got the grams per mole. MgO. So I used this. I'm going to use this. And the molar ratio I used was between these two. 2 moles of Mg to 2 moles of MgO. So that's the molar relationship for the reaction. So now we use this. Moles of MgO. Moles of MgO, 1 mole of MgO is 40.31 grams of MgO. And this that's the theoretical. And once we get that, the rest is easy. 13.1 times 2 times 40.31 divided by 24.31 divided by 2. It's going to be 3 significant figures, and I've got 21.7. 21.7 grams of MgO. There's our theoretical. Actual yield is given. To find the percent yield, it's always actual on top over theoretical times 100, and that's your percent yield. So in our case, actual is 12.4. 12.4 grams of MgO. Theoretical was 21.7 grams of MgO times 100% equals, and notice grams of MgO and grams of MgO cancel. The only unit left over is the percent sign. 3 significant figures, 3 significant figures. This is exact. The 100 is exact. It's by definition out of 100 per percent.
With the 2 MgO, are we just like kind of ignoring that, or is that 12.4 grams?
This, the 2 MgO.
Yes.
What's your question?
Like, is that what we're calculating? Like, is that the 12.4, or is it just MgO, 12.4?
Just MgO. The 2 is telling you the ratio of these things to each other. But once we're down to the end, 21.7 is just how much MgO there was. It's not how many pairs of MgOs there were, it's how many MgO units there were. 12.4 divided by 21.7. That times 100. To 3 significant figures, I got 57.1. So this 57.1 is kind of a reflection of the method used to do this reaction. There's probably some more careful methods that can be done to get a better yield. But theoretically, we should have gotten 21.7 grams out of it. But whatever method was used to do this reaction was kind of lame, and this is all I got. We will do reactions in here and calculate theoretical yield. I'm going to upload a tentative lab schedule, but I'm sure Monday we won't have a lab. The next Monday is a test, so we won't have a lab. So I'll give you guys plenty of warning when we do another lab. We really don't do too many labs in here. I'm going to make it. Okay, what else I got? That's 66. Let me mention something about 65 if you're going to practice it yourself. Let me do some erasing. You guys good?
Yes.
Can I erase? if you do 65 for practice, it uses ions, which might be distracting. It goes, that thing is. So this reaction, Pb2 plus 2KCl makes PbCl2 plus 2K plus. The ions show up in the equation. I just want to mention that you still just look up the periodic table for Pb, which is really heavy, grams per mole. So you use that for Pb. And for K, you just look it up on the periodic table, K plus. And that's so don't let the fact that it's ions confuse you. Everything else is the same. For number 67, what I'll need for you for practice, things they're not clear about. NH3 is called ammonia. They don't mention that. They show you how. They also, they're using kilograms. And I'll do one that uses kilograms, but I will tell you, just take all those kilograms, convert them to grams, and then write those below the thing like I was doing. And then everything else is the same. You just do that conversion right up front and it's out of your way. But I'll do one that uses kilograms next. 68 doesn't give. 68 is one of those that gives you the answers to. But it doesn't explicitly give you the reaction. So I'll go ahead and do that one. Silicon is 28.09. Straight from the periodic table. So let me do 68. Here's what they don't give you, but I wish they did. But they made a word problem out of it, so here's what it comes down to. 2 carbon atoms makes pure silicon plus carbon monoxide. And it refers to this as the product. And it says 177.4 kilograms. And it says 100.1 kilograms of carbon. And it tells you kilograms that side was collected. And this is again going to be the actual yield. So these are the things that are given in the problem. I would say, because what comes off the periodic table and what we calculate for the grams per mole for stuff is in grams, I would say just go ahead and put these in grams. Ultimately, the conversion turns it into, moves the decimal 3 places. So this ends up being 400 grams. This one ends up being 100 grams, and this one ends up being 712 grams. So this is like 67. I would say go ahead and turn your kilograms into grams, and then set it up like this to solve it. And that gets that conversion out of your way right up front. So here's what we've got. It was kilograms because this is an industrial scale reaction. Okay, so you have this many grams of SiO2, this many grams of carbon, and what they actually collected at the end of the reaction is this. So our first step, we're still doing this, we have to find our limiting reactants. I guess we could go ahead and get grams per mole and stuff. Two times 16 is 32. Six, so. This is right, 60.9. So we need grams per mole of both of our reactants. Carbon straight off the periodic table, 12.01. There's SiO2. It's 12.01 grams of carbon is 1 mole of carbon. Ultimately, we're going to need Si as well, but our product is just this, so that's. We're going to need that eventually as well. All right. All right. Pick one. We got to find the limiting reactant. I'm just going to pick SiO2. And go 177,400 grams SiO2. Grams of SiO2 on the bottom. 60.09 grams is 1 mole SiO2. Now we need the molar ratio of the two reactants. Moles of SiO2 goes on the bottom. 1 mole of SiO2 to 2 moles of carbon. Now we need moles of carbon on the bottom. And we're going to use this. 1 mole of carbon is 12.01 grams of carbon. That's going to give us grams of carbon. This is what we need. This is what we have. All right. 177,400 times 2 times 12.01 divided by 60.09. And that's it. And I got to 4 significant figures. I got 70910 with no decimal. All right. We need 70,000 or so of carbon. We have over 100,000 of carbon.
Are you gonna specify to them like how many sick days they need to answer, or do they need to be able to get that from?
It's the same rules as before.
Okay.
If you look at this, 4 significant figures. If you look at this, that's 4, because there's not a decimal here. This one is, this one was actually a 3, I think. But that's a little confusing because you have to use scientific notation there to do that one correctly. But since it's going to be multiple choice, it's not going to be that difficult to do significant figures. The place on the test where I test for significant figures is just testing for significant figures. Once we get to stuff like this, it'll be a little easier. I won't try to trick you about significant figures.
Perfect.
Okay, so what's our conclusion? We need 70,000 or so. We have over 100,000.
That's the excess, 70,000.
So this one is excess. This one is limiting. So now we found our limiting reactant. The next question is theoretical yield. And again, I can just leave the SiO2. So SiO2 turned out to be the limiting one. I can leave this stuff. I'll finish it out. Now we're finding the theoretical yield. So I'll first write down the grams of SiO2, and I need the grams per mole for SiO2. Now I'm relating the limiting reactant to the product. The product here is specified as Si. That's in the problem. That's how I knew that this is the product we're after, not this one. 1-to-1. One mole of silicon and 1 mole of silicon is down here, 28.09. And that'll give us our theoretical yield in grams of silicon. One 77400 times 28.09 divided by 60.09 equals, I get, if I'm doing 4 significant figures, 82,000 and some. But this is the actual yield you got, 71.200. And like I said, that's typical to not quite get all of it. Most of the experiments we do in here can usually be closer to like 97, 95, 99. Some of these industrial processes are not quite as clean. So we've got the theoretical yield. That's our theoretical yield. 82,930 grams of silicon. This is our actual yield, so we can now calculate our percent yield. Actual was 71200 grams of SI. And theoretical, what we should have gotten in theory, 82,930 grams of silicon times 100%. I get 71200 divided by 82930 times 100, and I get 85.9%. Into that column. 68. After you find the percent yield, you take a sip of your energy drink. I got their energy drink? No?
Yes.
Take a sip of what you got. Shot of tequila. Oh, my dad's coming home this afternoon. No complications. They were very careful about everything, and now he gets to go home. He's still got some recovery to start moving around again. But truthfully, they didn't let him move around much in the hospital, so now he's going to get to move around, and that's going to be the final step. Speaking of turning up a drink. All right, what I want to do next let's review that. And we have plenty of
He's a huge chunk. He got all You wouldn't die for that. Are you going to die for that?
I, of course, don't have any of these up yet either for y'all to see. Pull some out for you to practice.
They tried to get us out. What, getting established? Oh, no, it is true. Because a lot of them shooting at I go by the Bible. She was like,
For like 20 years ago. Probably not kids. It's like, how they
Like, based off of how inflation is. That's why it's like,
do you know the figure that they put on the you know they found a dead body in this car, right? And they have to stop tour. Look at the chopped up dead. No, I'm not saying he did it.
oh,
No, someone stole his car.
like, you were stolen, but now they found it.
No, he was on tour. He's been getting on his whole on his whole
history before? I'm sure you remember the word molarity. And you love that concept just as much as you did moles. I know you didn't. But here's your second chance to grasp it.
I just wanted to.
Empty your cup. Start over. You guys ready? You guys, molarity ready? Guys, ready? Molarity. Molarity is defined as moles in 1 liter. So for instance, if you had something that was, well, let me write this first. Let me say something about the letter M that stands for molarity. If someone says, a solution is that concentration, go ahead and forget that M. It's not needed. I don't know why it was invented. It means moles per liter. When you see a problem that's got an M in it, go ahead and rewrite it like this. And then of course, the way I always tell you, in 1 liter. When you see this, don't let it screw with you. Go ahead and get here, because this is how you're going to calculate it. And then you can see what we're talking about. It's 0.916 moles in 1 liter. That's the concentration. You can have less than a liter. I know that's confusing too, but if I said I traveled if I traveled 65 miles per hour, and note there's no special letter like the M, which is good, it means miles per hour, it means 65 mile. If I told you I traveled 65 miles per hour to get here, I live here in town, so I'm being really dangerous if I did that, but if you made a trip and you traveled 65 miles per hour, and I got to wherever I was going, I walked up to you and I said, I went 65 miles per hour all the way here. You wouldn't think that what I'm telling you is I traveled 65 miles. I could have. Would have been a coincidence. And it would have taken exactly an hour. If I came up and told you I traveled 65 miles per hour coming here, but I traveled for like 8 hours, you wouldn't be confused. You would know it doesn't necessarily mean I traveled for an hour. It doesn't necessarily mean I traveled for 65 miles. So I could travel 65 miles per hour in a quarter mile, less than a mile. But I would still say 65 miles per hour. And you wouldn't be confused by that. I could travel thousands of miles at 65 miles per hour. That doesn't confuse you. You just know that I went a long way at this speed. This is similar to concentration. 0.16 moles per liter, I could have a tiny amount, not even close to a liter, and it can still be this concentration. It's just saying, if I had a whole liter, there would be 0.16 moles in it. So don't let that confuse you. Just work with it this way. Work with that for the math. So that's the definition. And like I said, just replace that in, think like this, write it like this, and then these calculations you'll be fine. I'm going to go through the even ones here. Starting with 22. I'm going to do 22, 28, 30, 32. I guess I can add 33 and 34. So I'm going to do 34 as well. And I think you're okay with the odd ones, because they'll be just like the even ones. Right. This is 22. Calculate the molarity of It's not exactly word for word how 22 is stated, but that's what it's asking. I should say moles of. All right. Notice grams or mass is not mentioned. That means you're not going to even really have to calculate anything related to this. This could really be anything. In the same way, a mole of, the number of things in a mole is 6.02 times 10 to the 23rd. Whether it's grains of sand or carbon atoms or whatever, it's 6.022 times 10 to the 23rd. You're given the number of moles of whatever it is, and you're given the liters, so you can calculate the molarity out without dealing with the actual identity. And because of the definition, molarity is moles over liters. All I have to do here is go 0.55 moles in 9.56 liters and just print it. 0.55 divided by 9.56. 0.55 divided by 0.56. And I get, and I guess I'm in two significant figures here. So my calculator says I'm keeping these, so the 5 rounds to 7, so the 7 becomes an 8, and all of that goes away. And then you just keep your units, moles per unit. That's the answer. You might see, for the multiple choice, you might see, but like I said, the capital M just means moles over liters. It's a superfluous thing. I wish it didn't exist, because it just makes it a concept that's a little bit nebulous even harder to crack into. But that is 22, that's A for 22. Right. This was A on 22. B for 22 is, now this one involves a twist. Calculate the molarity. Better erase all this. Grams of C2H6O in I forgot a little vocabulary I better mention. Do you remember solute and solvent from before? If I have a solvent, it's almost always water. And then I have some stuff, like let's say it's C2H6O, and I sprinkle it in there and it dissolves. The thing that I'm sprinkling in there is called the solute, and the water is called the solvent. We almost always use water because it's cheap and easy to get rid of, and et cetera. But you can use alcohol. Anything that's liquid can be a solvent. It's almost always a solid that we're putting into the solvent and it dissolves. But you can also pour a liquid into a liquid, and as long as they're miscible, as long as they dissolve together, then you can have a liquid solvent rather than a solid, a liquid solute rather than a solid solvent. But think of these as the solid, the little bit of something you sprinkle into a solvent. I don't think this even mentions what the solvent is. It's probably water. But it's saying the solution when you're done. Okay, so the specific definition of solute versus solvent is whichever one there's more of. So if you have exactly 50-50, it's unclear what the solvent and solute is. But there's typically very, very, very little solute and vast bulk comparatively solvent. So definitionally, The solute is what there's a tiny amount of that you've dissolved in, and the solvent is the bulk liquid that you've dissolved it in. Once you do that, then it's called a solution. A solution is a combination of a solvent and a solute dissolved into. Just a little vocabulary, but I'll end up using. All right, what is the molarity? All right, this time grams is mentioned, and like I keep saying over and over, whenever grams is mentioned, you're going to need the grams per mole of the thing. So I'm going to need the grams per mole of this, meaning carbon, there's 2 of them. Hydrogen, there's 6 of them. Oxygen, there's 1 of them. 12.01 from the periodic table, 1.01 from the periodic table, and 16 from the periodic table. This will be 24.02. This will be 6.06. This will be 16. 6, 7, 8. That's 6, 7, 8, 0, 12, 13, 14, 16. 46.08 grams of C2H6O is 1 mole. 6O. So we're going to need that. So when grams is mentioned, you pretty much always are going to need the grams per mole. And notice concentration, molarity is moles per liter, so we're going to need a relationship between grams and moles here. So the way to do this, we need 55.6 grams C2H6O. And then we're going to need the grams per mole, which is 46.08 grams C2H6O to 1 mole. And that's going to give us moles. All that's left, we've got moles and it's on top. All that's left is we need to put the liters on bottom. And I'll say liters of solution, or I should say liters of C2H6O solution. And that'll do it. All the units are in place. So if you're given the grams, that's how you calculate the molarity, given the amount of solution that's there. That'll do it. That'll give you the moles per liter. You see how the units cancel? Grams of C2H6O, grams of C2H6O goes away. Nothing cancels out the moles, and nothing cancels away the liters. That'll give you moles per liter. 5.6 divided by 46.08 divided by 1.94, and 3 significant figures, 4, 3. That's exact, that's exact, that's exact. We've got 3 significant figures, 4 and 3. I end up with 0, 6, 2, 2 moles per liter. Which means is, what that means is if you get, this is not quite right, but if you got 55.6 grams on the scale of this out of a bottle that has this label on it, and you measure out 1.94 liters in some vessel, and you put those grams in it, your concentration will be 0.622 molar. And I'll write this with the capital M, just so you see them side by side. But it can be also written that way. But I'm telling you, there's no reason for the capital M to exist in science. I wish it was never invented because it's superfluous. I mean, when we do density, we do grams per milliliter. There's no special letter that you stick over top of that. It's just grams per milliliter. If it's moles per liter, why not just leave it as moles per liter? Why have it in anyway? I'm not going to win that battle because it's everywhere in chemistry all the way around the world and has been there for decades. I think it helps to say out loud that that's just superfluous. I wish it wasn't there. You agree with me, Lucy? Lucy looked over and
Yeah.
smiled.
I'll start a protest for extra credit.
We won't win.
You get the movement.
It's us against the world. Anyway, so that's how you do that calculation. Given grams, that's how you find the molarity. That's B on 22.
And you really can just think of that as like moles over liters equals M. You put moles over liters, it's the same thing.
It's the exact same thing. It's literally,
So we won't pick off on the test if you put either or.
huh?
Since we can probably don't pick off on the test if they put either or. 'Cause they're just-
You could put either or, yeah. But since it'll be multiple choice, I'll try to remember to do this, but if I do this, just don't be confused.
What did this mean?
All right, what are we doing? Okay, this one only has a small twist. You can sometimes, instead of be given grams, you can be given milligrams. And sometimes instead of liters, it's milliliters. So this is C. This is 22C. 15.32 of LIVR is 243.6 milliliters of solution. This is milligrams, so that tells you you're going to need grams of this. You have to look at the periodic table. Lithium is here, 6.94. Bromine is on the right side, 70.99.
Come get me some special information.
So this calls for the metric conversion factor. I need this in grams. I need to go from milligrams to grams. Or let me put the LIVR in here. I'm going to need to go from milligrams to grams. The way I would do this is I would say 1,000 milligrams is 1 gram. Now we're in grams of LIVR. Now I can use this. There, now I've got moles of LIVR on top, which is what I want. Milligrams cancel, grams cancel, I've got moles of LIVR on top. Now I need to get liters on the bottom. I've got 243.6 milliliters. So I'm going to need 243. I'm just going to say solution, but I mean lithium bromide solution. I'll just put a 1 there. I need to convert to liters. I need liters on the bottom. If I get milliliters on top, and it will cancel. Instead of solution, I should probably say in parentheses, but what it is in context here. 1,000 milliliters to 1 liter, and that'll do it. That'll cancel down to molar per liter. The 1,000s do cancel. If you're thinking, well, let's just ignore those. I write them out because you might have been given the last one in liters, and then you wouldn't have a 1,000 there. It would also work out to go and just throw that in there, and then you wouldn't have to do the conversion. But if you just faithfully calculate that out, that'll give you the molarity. Let's see what we get. 15.32 times 1,000 divided by 1,000 divided by 77.84 divided by 243.6, and I get these are exact, both of them. That's exact. That's exact. That's exact. And both of these are exact because they're metric to metric conversion. 4 significant figures, 4 and 4, so I need 4. My calculator says there's my 4. The 3 doesn't round to 9, so I can write this. That's the answer, moles per liter. I could put it in there instead of the moles over the liters. Maybe you'd probably want to put this in scientific notation. If I told you to put your answer in scientific notation, you would go, and it's 1, 2, 3, 4. Concentrations tend to be kind of small like that. Molar concentrations.
So like you said, if we wanted to go ahead and convert those milliliters to liters and then solve and see that.
If you did this ahead of time, this is what you're saying, then you would just put
Just give
here,
that part.
and you wouldn't bother with that. That would do it. If you wanted to just do that ahead of time. 1 grams. And if you did that for grams, you could put that in here. It's liters. If you just wanted to convert that and then stick it in, then you could go 0.01532 grams, and then you wouldn't need this. And then you've got grams of LIVR, grams of LIVR, it will cancel. So you can sort of preload by doing your conversions ahead of time. I like to stick it all in one equation just so it's all there on the board to see. Okay, 22C. Oh, what is 28? Okay. Here's a fun variation. This is 28. Okay. It mentions mass. So as you can imagine, we need the mass of this. Don't forget that you can just do this. Replace the M with the moles over the liters. Maybe that helps. The way this one starts, 0.55 liters of, I'm just going to say solution, although I should say this. Solution. Moles per liter, this means in 1 liter. This will make the liters cancel. Moles of that in 1 liter solution. So now we're in moles. Since we're trying to get the mass, that is grams, the only thing left is the grams per mole, and that'll tell us how many grams. So you've got a solution, you've got 0.55 liters of it. Its concentration is 0.110 moles per liter. This could have asked how many moles are in there, and that would be the calculation. Surely I have one of those. Calculate the moles of this in 0.55 liters. So notice, if you just multiply this by this, the liters cancel, and that'll give you moles. Multiply this by this, the liters cancel, it'll give you moles. So if this question asks how many moles of C6H12O6 is in 0.55 liters of this concentration, that's all you need to do, that'll give you some moles. See that? This is asking for grams, so you need the grams per mole relationship, which means you need 0.06. No way I'm doing that in my head. 6 times 12.09. This one will be 12, 6 times 16. If I did that right. That'll do it. Liters of solution cancel. Moles, C6H12O6 cancel, and we end in grams. So that's how you would solve 128. .55, 0.110 183.18. And there's nothing to divide by. Two significant figures there. So the answer is 11. That's how we solve it. Ask for the grams of the solute. Okay, 1/30. So if you ask for moles, that's all you need. That would give you moles. It's just the liters and the moles per liter. You can get the moles by doing that. If you're asked for the grams of the solute, then you need grams per mole to do it. So ask for moles, ask for grams. What if you're asked a volume? Ask for volume, this is 30. Calculate the volume. C12, H22, O11. God. 12, 2, 11. To solve that, it mentions grams, so you're going to have to find the grams per mole. Coming up with 342.34 grams of C12, H22, O11 to 1 mole of H22. We're going to need that. Right? To set it up. C12, H22, O11. We'll use the grams per mole here to get moles on top. I'm trying to get to a volume. So I'll put moles on top. We don't want to start with that. To find the volume, moles on bottom. All right. Let me start like this. We're trying to find a volume, and I'll say liters, and everything else needs to cancel. But this means this, and you can also write it as 0.200 moles in 1 liter. Since I want everything to cancel out except for liters, I'll start with that. 1 liter of the solution moles C12 H22 So there, I've taken this and flipped it over to start so I can get a liters on top. And now I'm just going to go about trying to get everything else to cancel. The only thing I've got left with moles in it is this, the moles of the C12, etc. So I'm going to put 1. Top and 342.34 grams of C12H22O11. All right, so now I've got moles to cancel away. I need grams to cancel away. And I'll do it with this. And that, I think, does it. Moles of this cancel, grams of this cancel. I've got nothing but liters left. And I've used everything. That'll do it. $55.8 divided by 0.2 divided by 342.34. Exact, 3 significant figures, 5, that's 3 significant figures. So I'm going to keep 0.815. Grams of that cancel, grams of that cancel, moles of that cancel, moles of that cancel. We end up in liters of solution. We end up in this unit. So that's how you find the volume given the grams. Ugh. So 31 is similar to 32. 29 is similar to 30. What is the mass of copper nitrate? Copper 2 nitrate. Molar solution. Our ingredients here, we're asked for mass, so we're going to need the mass of this. The grams per mole, that is. We do that over here. Cu, we have 1 of them. Nitrogen, we have 2 of them. Oxygen, we have 6 of them. Copper. 63.55. if I did that right, we've got would be 7.57 gram CU into 3.2 mole of CU into 3.2. This is going to be involved. Other factors that will be involved are this 0.150 M is the same thing as 0.150 moles per liter, which is the same thing as 0.150 moles over 1 liter. That's the way I'm going to use it. And I'm just going to say solution. I should be saying
I think the camera's kind of like blurred now.
I fixed that this morning. Oh, come on. I'm making the camera tired. All right. So we're going to need that. We're going to need this. It comes from here. And we're going to need the 155 milliliters. You want to go ahead and turn that into liters? 0.155 liters. We'll use that. And we need all that to cancel down to grams. This is where the grams are, so I'm going to put this first just so I know I've got the grams on the top. Grams of CU NO3 I need the moles to cancel. I've used this. This has moles in it. So I'm going to put the moles on top so they'll cancel 0.150 moles of solution. Moles of CuNO3 in 1 liter of solution. Now, if I could just get the liters to cancel, we'll have the grams. That's in my way. And there's the liters. Solution. That'll give us the mass copper nitrate, copper 2 nitrate, and 155 milligrams of this concentration copper 2 nitrate solution. Times 0.150 times 0.155, nothing to divide by. 5 significant figures, 3, 3, so I need 3 there. 4.36 is what I get. Grams of CuNO3. I'm going to do one more and then stop. Exactly like this one. SRVR2. used to make sorry, can I erase this?
Yes.
This next one is exactly like that one. We're trying to calculate the mass. Mass is mentioned, so we're going to need the gram per mole of SRBR2. SR, there's one of them. BR, there's two of them. SR, periodic table. SR is down here, 87.62. And BR over on the right, 79.90. 1 times 87.62 is 87.62. 2 times 79.0. $79.90. 159.8.
That's weird. 2, 18. If I did that right, I've got 247.42 grams. SRBR2 is 1 mole of SRBR2. So I'm going to need that because grams is mentioned, we're asked for a mass. 125 milliliters is 0.125 liters. I'll use that. This is 0.200 moles per liter, aka 0.200 moles of SRBR2 in 1 liter of solution. And instead of solution, again, I should probably write SRBR2 dash solution, just to mention what kind of solution it is. But because of context, we know that it's SRBR2 solution. So there's our ingredients. And we need those to cancel down to grams. So I'm going to put my grams first, just so I know they're on top. Grams of SRBR2 is 1 mole. Now I need moles to cancel. Moles are here. 0.200 SRBR2 to 1 liter of SRBR2 solution. Now if I can just get the liters to go away, I'm down to grams. Here's our liters. And that'll do it. $247.42 times 0.2 times 0.125, nothing to divide by. We're still in 3 significant figures because of this and this. And I've got 6.1. Stop there. Lucy, I'm going to do the dilution formula next. The dilution formula, N1B1 equals N2B2.